All right, welcome to lesson three. Today we're going to talk about one of the most important probability distributions, and hopefully you'll remember a good many of these things about this probability distribution, but it's one that we're going to use repeatedly throughout the course. And so we'll just dive right in to start to talk about the normal probability distribution function. And again, you will see, and hopefully you will remember, that the normal distribution is represented by this bell-shaped curve. It has, as a matter of properties, it's described by two parameters. And the first parameter is mu, or the mean. It's the average value of the distribution. And the other parameter, if you will, I will say this, the mean, the mu, describes the location of the center of the distribution. And so as you see here, we're measuring some random variable we'll call x. And it's measured on a continuous scale which will go from negative infinity all the way up to positive infinity. But the mean of this distribution happens to fall right at this point, or that's the center of this distribution. So it's the location. And then the other parameter is the standard deviation, or it's represented by the Greek letter sigma, which is this symbol here, mean and standard deviation. And the standard deviation, is shown in the graph, represents the width of this distribution. And so that perfectly describes the distribution function of this random variable in that bell-shaped curve. All right. Additionally, the way that we calculate probabilities is as follows. The distribution function, which is the p, these are lowercase p df. The probability distribution function is this curve. There's a mathematical function that's in the handout that describes that curve. And the parameters mean and standard deviation will result in this, when you substitute those in, result in this curve. Now, the way that we determine, or where we calculate the probabilities is we calculate that by determining the area underneath the curve. So let's say, for example, if this is a value of 10, if the mean is 10, and we wanted to know what's the probability that this random variable turns out to be less than or equal to 5, then we have to calculate, and my drawing is not very good, but we have to calculate this area under this curve that's below or to the left of 5. And that's not a trivial thing to do. It requires calculus, and it's not a trivial thing to do. So the question is, unlike for our exponential distribution, which we can, in a closed form, calculate the probability. Remember that we had a random variable t was less than or equal to t. If you remember this, this cumulative distribution is represented by 1 to minus e to the minus lambda times t. Well, that's not the way this works here for the normal distribution, because this calculation to the left of 5 in our case is not a trivial calculation. So then our question becomes, how do we calculate this area? Well, the next thing that you'll want to remember and recall is that the total area under the curve is 1, or 100% is the total. area. All right. And then the next fact, as you'll see, as you can see from the distribution is symmetric around the mean. And what does that mean? And that means that the shape is a perfect mirror image from to the left of the mean and to the right of the mean. Those shapes are perfectly identical. And of course, in terms of probabilities, everything to the left of the mean is 50%. Excuse me, my drawing doesn't match my words. Everything to the right of the mean is 50%. And similarly, everything, the probability to the left of the mean is also 50%. So that's what we mean by symmetric around the mean. It's identical shape and identical probabilities on either side, which is an important fact as we start to use our distribution. Okay, so let's step to the next slide. One of the things that you'll notice as well is that the parameter values, the mean and the standard deviation, describe the combination describes an infinite number of different normal probability distributions. So in this case, this example in the upper left here, if the standard deviation is small, that means this value is, the width of this curve is small, then results in a tall and narrow distribution. If the standard deviation is large, again, you can see that this, just by the scale, that this standard deviation is larger than that standard deviation, then it creates a wider distribution. So it defines the width. Now on this scale, on the bottom two graphs, we have a random variable. Again, we're going to call x, and just let's say hypothetically this is the height of we'll say this is the weight of men and women. And in fact, in this case, you'll see the standard deviations are approximately the same. The width here is approximately the same. But in this case, the mean is smaller. So this would be, if you will, women, and perhaps this is, the average here is 120 pounds on this scale of weight. So we're measuring pounds. And perhaps for the men, this mean is 175 pounds. And so the mean of the women's distribution is smaller than the mean of the average weight of this distribution. So again, putting all these together, depending on the values of your mean and standard deviation, that creates potentially an infinite number of normal probability distributions. So then the question is how do we deal with that, since there's an infinite number? So here's the result. There's what we are going to call a transformation, and we're going to transform any normal distribution into what's called a standard normal distribution. And for the standard normal distribution, it still has that bell-shaped curve, but the standard normal distribution, the mean is always 0, and the standard deviation is always 1. The mean is 0 and the standard deviation is 1. And so that means everything for the mean, and we call this value the z value because it's just a variable that we're going to give. Everything to the right of the mean, to the right of 0, this value of z is positive. And of course, everything to the left of the mean for this standard normal distribution is negative. And again, every normal distribution, or any normal distribution, can be transformed to the standard normal distribution using what you may remember as the Z transformation. And we'll talk about that more in the next slide. And then once that generic normal distribution is transformed into our standard normal distribution, we can use a table. We can use a table to determine the probabilities. All right, and that's the process that we're going to go through. All right. So let's go to the next slide and look at how this works. Here's a standard normal, or excuse me, the top curve is just a generic normal distribution. And again, you'll see the parameters are some value of the mean and some value of the standard deviation. And then what we're going to do is we take every value on this x-axis, or a value on this x-axis, and we substitute in this value for x, a value for the mean and a value for the standard deviation. We calculate a value of z, and we're going to use that z value, and what that does is that converts this distribution into a standard normal distribution with mean of 0 and variance, standard deviation of 1. And then we're going to use this to calculate the probabilities that we want to calculate and use, and those are tabulated. Okay, so these probabilities again correspond to the area under the curve. So for this particular value, which would be some value of z, then everything less than z is this area, light blue area under that curve, and that's in our table. And we're going to, again, we'll review how this process works on the next slide. So here's what one of the tables that you see, and I've color coded this so that what I want you to remember is two things. Number one, the area under the curve are the area represented by blue. The blue area is the area that corresponds to these values in the table. And the z values, when you calculate the z value using our transformation, those values are read on the row and column of this table. So to use this table, once you have the z value, and let's just for argument's sake, let's say our z value we calculate to be 1.78. And how this is broken down is the first part of this table is 1.7, which is our z value, and the second part is 0.08. And if you add those two together, that's 1.78, which is our z value. All right, z value is 1.78. Sorry about that. But so to find the probability associated with these z value, we're going to look for 1.7, and then in the column 0.08. And that where these two values intersect, that's the probability that's associated with this value. And you'll see here, if you can read that, it says 0.9625. So 0.25% is associated with this z value of 1.78. Okay, so hopefully that will remind you of the process. Now, I do want to point out there are two different tables that are placed in the D2L in the lesson folder for lesson 3, and one of which looks like this, except it's just black and white, and it doesn't have the blue and the yellow. And you'll notice this only has values for a z value that's greater than 0. Everything here in this column is greater than 0, and every value in the row is greater than 0. So it only provides values of z for z greater than or equal to 0. And again, if you can see if z is 0, then the probability is 0.5. Because the mean here is 0, and there's and so it only gives probabilities associated with things that are with outcomes that are greater than or equal to 0. But you can, because it's symmetric, you can manipulate this to determine if you know what this probability is, and let's say as it was before 0.9625, if this was our value of 1.78 here, then you know by the complementary property that everything that's in this white area is 1 minus 0.9625, and if my arithmetic is correct, that's going to be 0.0375. So again, you can manipulate this and determine any probability with just this table. We're going to look at some examples for that, so don't be concerned. There's another table, and this is 2 pages. It looks like this, and if you look carefully, you'll see the z-values here are all less than or equal to 0. So in other words, here's negative, where's our negative 1 point, let's just see if we did our arithmetic correctly. Here's negative 1.7, and here's the 8. And so the intersection of those, whoops, 1.7, 8. Let me start this over. I got, here's negative 1.7, 8, and that's 0.3754, which was, it's a little bit different. It's that's the same, 0.0375, and this has got an additional decimal place. It's got a 4/10 thousandths decimal place, so that is exactly the same, 0.03754. All right, so those, it has the values for negative z as well as on another sheet, the same table that you saw before, the positive z's. And again, here's 1.178, which is 926, and of course this would round to 5, 9265 that we had in the other table. So point being, you can use either table that you wish. They're both correct. You can use your calculators. That's correct. And there's a third table in your textbook which you can use, but I would recommend using one of these 3 tables, either these 2 that are here or this other table that's shown, that's only the positive values. All right. So let's work a couple of examples. I want to say, just as an aside, I've been doing this a really, really long time, And I understand it forwards and backwards, but I will promise you, every time I do one of these problems, I always draw the normal distribution. And it doesn't have to be perfect like the one I'm showing. Normally, I'll just draw something that looks like this, and I'll use this drawing to help guide me with what I want to do. But I really encourage you to draw the diagram. It will help keep you straight. All right, so let's see how we excuse me, can work one of these. So we're given a random variable x. It has this n means that it has the normal distribution. The mean value is 42. The standard deviation is 8. And we want to find the probability that that random variable is less than or equal to 53.4. So in order to use the diagram, and of course the 53.4, this corresponds to the value of x that we're going to use in our transformation. All right. So the first thing that you want to do is just label your diagram. And we know that the mean is 42. We know, and it's going to lie right here. Know that the standard deviation is 8. And we know that where does 53 fall in relation to 42? Well, somewhere, it's going to fall somewhere to the right of 42. So here at this point, somewhere over here, and again, it doesn't have to be terribly accurate, just something to guide you, 53.4. And we want to find out the probability that is less than or equal to 53.4. And you can sort of follow the diagram. The less than or equal to means that's going to be everything that's below 53.4. And then finally to find this probability, that's going to be everything that's under the curve that's to the left of 53.4. That stays under the curve, actually. So it's everything under the curve. And so now we're going to need to use our Z transformation, and we're going to substitute in here. We said already the value of x is 53.4. The value of minus the mean, which is 42. And then divide that by 8. That's going to be our Z value. And so 53.4 minus 42 is 11.4 positive divided by 8. And so that Z value is 1.43, rounded up, because we're only going to use 2 decimal places. It's actually 1.425, but this Z value is 1.43. And so this corresponds to a standard normal distribution value where Z equals 1.43. And so now we're going to go to our table on the next slide, and remember 1.43, and we're going to look up that value in the table. And here's 1.4, and here's 0.03, and where those two values intersect is the value of our probability. In this case, it's 0.9236. And that's our answer. The probability is 92.36%. All right, let's go to another example. And in this case, we know we're given our mean and standard. Actually, we're not given standard deviation. In this case, we're given the variance. And notice, let me erase this. Notice that in this case, instead of the standard deviation, we're given the variance, or sigma squared. And so sigma squared is 16. And we find the probability that x is greater than 8.52. And so now, using our information, we know that the mean is here at 15. Our x value is somewhere below 15, 8.52. And we want to find the probability that x is greater than 8.52, so it's everything above 8.52. And again, the probability that's under the curve is everything that's under this curve that's above 8.52. Okay. Now we're going to again use our z transformation. X is 8.52. Our mean is minus 15. The mean is 15, but we're subtracting that from the x value. And then we're dividing by sigma, not sigma squared, so we have to take the square root of 16. Because this is sigma, this is the standard deviation, and it's not the variance. And so this is going to be, of course, you know the square root of 16 is 4. 8.52 minus 15 is negative 6.48 divided by 4. And this is negative 1.62. Negative 1.62. Okay, so now let's, how are we going to use our table? Well, there's two ways that you can do this, but let's just use the single table to see how we can manipulate the values here. So let's go at this table. Again, remember these are positive values, but if we look up 1.62, 1.6, and then here's the column, and go across, and here's 0.2. The value that corresponds, we go back to our problem, even though it's not going to, the value that corresponds to a positive 1.62 is 0.9474. That's the probability that corresponds. And so what that means is that the probability for a positive the probability that's less than positive 1.62, that probability is 0.9474. And what I'd like for you to try to realize is that that probability, let me redraw this first of all. So what we looked up was the value was positive 1.64, not negative 1.64, or 1.62. We looked up positive 1.62, and we know that this is 0.9474. Okay, now we're together. And that was everything under the curve to the left of positive 1.62. Well, what did we want to find? If you remember, we wanted to find everything that's to the right of 8.52, which was negative 1.62. And if you'll, by the principle of symmetry, everything that's above positive 1.62, see if this makes sense, everything that's above positive 1.62, which is our red, is exactly the same as everything that's below positive 1.62. So the answer that we're looking for is, in fact, the answer we're looking for is 0.9474, which is the probability that X is greater than 0.8252. All right, so now let's look at another example, and I believe this is our last example, and it's a little bit different because now we want to find a probability. We want to find X, not a probability. We want to find a value of X given a probability. And what we know right off the bat, of course, again, is that our standard deviation has a mean of 200 and a variance of 144, which means, of course, that the standard deviation is the square root of that, which is 12. But here's the question. We want to find X so that the probability that X is greater than or equal to X is 65%. So how are we going to use our diagram to help us solve that problem? Well, the first thing that we're going to do is the following. We want to know about this 65%. This is an important value. And we want to find X somewhere so that the probability is 0.65. Well, we know everything above 200 is 50%. So this X has to be somewhere to the left, because what we need here is another, again, is another 15%. And again, this is not to scale, but we need to find X somewhere over here on this scale so that we have another 15% to add to that 50%. And so what that means is, of course, 65% of the probability is to the right of this value, X. And so now, and again, as far as we know the value of our standard deviation in this formula. We know the value of the mean. We don't know what X is. We're actually solving for X. And but because we know the probability, we can look up this value of Z in our table. So let's go see how we do that on this next chart. So now we're trying to find a probability. So we're trying to find the area under the graph, under the curve rather, that corresponds to 65%. And to do that, you go into this table, we look for our blue probabilities, if you will, in the table, and find the value that's closest to 65%. So if we look in the table, here's 69, 62, or excuse me, 65, so it's somewhere 63.68, 64.06, 64.8, 65.17. So 0.65 lies between 0.648, and 0.6517. Now, in a math class, I would ask you to interpolate that, but for our purposes, it doesn't matter. You can choose one or the other, and we're going to choose the value of, and now once we choose this value, 0.6517 as being closest to 0.65, we read then the table, and we know that the z value, okay, is going to be, we know that the z value corresponding to this is 0.39. So that's the z value that we're going to need to use, except the following. Now, what do you notice? This value corresponds to everything that's below or to the left of positive 0.39. So what we want is everything that's what we want is everything that's to the right of this to be 0.65. And so actually our z value is going to be negative 0.39 that we're going to use in our equation. All right, so what we're going to do is we're going to solve for x. So negative 0.39 is going to equal to x, that's our missing variable, minus 12, minus mu, the mean, which is 200, divided by 12, which is our standard deviation. So now we do the little bit of algebra. So negative 0.39 times 12 equals x minus 200. And when we add 200 to both sides, so 200 minus 0.39 times 12 is going to equal to, that's going to be our value of x. And so that's a good thing, because as you'll notice, when we're going to subtract something from 200, which means it will be, the value x is going to be less than 200, which is a good thing. So let's do the calculation. And this is going to be x equals 200 minus 4.68, which is going to result in our value that we've been looking for is 195.32. 195.32. So those are three different examples. There'll be other examples that you can practice and work on. Again, as always, if you have any questions, please don't hesitate to contact me. Thank you.